Can that screen show this me now?
Do you want it to?
Yeah, or
You want to see yourself on that screen?
okay, maybe not. Okay.
So we have it set to speaker view. So if somebody was to ask a question, their face would pop up.
That'll perfect.
They have the
Okay.
camera on.
Okay.
Yeah, if they have their camera on.
Right.
So yeah, we could leave it set like this, or we could put it to gallery view. So
Okay.
then you'd see everybody's boxes.
Oh, this is fine.
A little harder to distinguish who's asking you a question.
Okay, let's see how it goes. Yeah, this is pretty legible, isn't it? Yeah.
It doesn't mute.
Yeah, this notice is for everyone here. These are rules that I got from the IAS. I'm allowed to remove my mask, so hopefully that's okay with you. I'm fully vaccinated, stay 6 feet away, and you're allowed to remove your mask to ask.
How do you prefer we ask questions? Just interrupt you or raise hands or wait till you ask questions?
Yeah, you can just ask questions, I think. So, all right, so it's 9 o'clock here and 6:30 in India. So hello, everybody. Maybe somebody remotely, maybe Kedar, can you say you're there? Hello, can you hear me? Somebody say
Hey,
something.
we're here in TIF Hyderabad. We're here. Yeah, you're being broadcast in a classroom. Yeah.
Is my audio on?
Yeah, it's on. Perfect.
Kedar or somebody at TFR in Hyderabad, just say hello.
Kabir, yeah, hi, this is Kabir. Hi, Shubir, can you hear me?
Maybe not hearing anything. Hello? Okay, I presume it's all right. Maybe this, you
Everybody's got their mic
can mute on, okay.
Can you unmute them?
Uh,
We initiated the Zoom.
I can unmute somebody if you want me to.
Well, you should.
Okay, maybe, yeah, somebody's.
Yeah, see, they can hear you.
Okay, all right.
Chatted.
Okay, that's one. All right, so welcome to the first Blackboard lecture of this course. This is the way the things are going to be every week. So as I said last time, registered students in India who are should feel free to unmute yourself and just ask a question, and hopefully I'll be able to hear it. As also the people in the live audience here at IAS. the others, well, we see how it goes. You may want to, if it's, I may tell you to put the question in the chat if it's going to cause too much of a disruption. Anyway. All right, so what else? Oh, yes, and hopefully you all have access to the website. There's lecture notes, there's the slides from last week, and also actually already the lecture notes for today's probably next week's lecture. So there'll be only lecture Wednesday this week, and the next lecture will be on Monday. And probably I'll talk to the people in India and try to get a problem set organized for the registered students sometime later this week. All right, so as I promised, what I'm going to talk about today is just a very basic system, bosons, just a single species of boson interacting with short-range repulsive interaction. It's typically useful to put the bosons on a lattice. So this, before about 2000, this wasn't really a realistic physical situation, but with the advent of ultrapole atoms, you can now take bosons with Bi and put them on some lattice. I'll generally assume we're in 2 or higher dimensions, although many things I'm going to say also apply in 1 dimension. So these are the Bose operators with the canonical Bose commutation relation. Ni is the boson number. So there's a hopping matrix element, which I'll call W. Repulsion between the bosons, any pair of bosons has a repulsion energy U, and mu is the chemical potential. So we want to understand the phase diagram of this model as, say, at 0 temperature, as a function of 2 parameters, the ratio of mu to W and the ratio of U to W. And that already gives you quite an interesting structure that we'll probably describe this week or maybe next week. All right, but to begin with, I'm going to consider the dilute case, or the weakly interacting case. So U is much, much less than W, and also some other parameters that will depend on the density that we'll specify more carefully later. So then there's some dispersion for the bosons, which you get by taking the Fourier transform of this W. There's a dispersion like this in the Brillouin zone. And if U is exactly 0, then the bosons will basically all occupy the 0 momentum state, the lowest energy state. So we'll put this at momentum 0. And near this point, I'll sometimes take, just call, this is a definition of M if you wish. I'll assume the dispersion is quadratic right at the bottom of the band. Okay, and that, of course, this theory, when I'm just focusing the bottom of the band, applies also to helium-4 where there's no lattice, which is where some of what I'm going to talk about first was initially worked out. So if I have n particles and the interaction U is exactly 0, then the ground state is you just put every particle, now this is K equals 0, in the 0 momentum state. So you have n particles, and we take as B dagger K equals 0 in the n particle state, and Bk is defined as 1 over square root of the volume, sum on I Bi minus e to the I Kr. Okay. So the Bk also, because of the factor of square root of volume, have the usual anti-commutation relation. Oh, sorry, commutation relation, but B's with different momenta commute with each other, and those with the same have unit commutator. Okay, so this is the ground state, and what are the excited states? Well, the excited states, if I plot the excitation, you can take a particle out of the ground state and put it into an excited state, and so it'll have a dispersion as a function of K, which will basically mirror this. So you can take a particle out of the condensate and move it up to some momentum k, and that will cost you an energy, which is, at least a small k goes as k squared. We're not going to talk about what happens up here, at least in today's lecture. Okay, so that's at u equals 0. Things are very simple. You can also turn on a finite temperature, and that you get a Bose-Einstein condensation temperature that was originally worked out by Bose and Einstein in the 20s, where where a macroscopic number of particles above the temperature are not present at 0 momentum. All right, so today what I want to begin with is the small u theory. That's often called the Bogoliubov theory. And one of the things we'll find immediately that no matter how small is u, this is not correct, that the excitation spectrum doesn't look like this, doesn't go as k squared at small k, but the actual excitation spectrum, which we're going to find out in a little bit, will be capital E of k as a function of k, initially goes linearly and then goes quadratically. So there's some regime here. This is for u not equal to 0, no matter how small, where it goes linearly with k, and then at larger k, it has a k squared over 2m dispersion. So what we'll say is that there's a qualitative change in this kind of excitation, which is just a single particle excitation, to what we sometimes call the collective excitation. And this particular excitation is often called second sound. So that's what I want to illustrate in the first calculation I'm going to present. Where does this come from? The modern understanding of this is really what we call a Goldstone mode. It's a low energy mode associated with the fact that the ground state breaks a certain symmetry, which is the symmetry associated with particle number conservation. And we'll see how that happens in this model at small u. This is called second sound, but that's a bit misleading in the sense that it's not like ordinary sound, first sound, which is really which happens when you have lots of collisions between particles. That's a true hydrodynamic mode in a regime where the frequency of the sound is much lower than the frequency of the collisions. This is really a coherent excitation. It's a collisionless excitation. Yeah, it's called second sound, but I would have called it something else. But anyway, that's what we'll start with. Okay, so let's see how this happens. It's small non-zero u. Okay.
So the second sound also in superconductivity, people talk about it?
So in superconductivity, when you have long-range interactions, this becomes a plasma. It goes to high energy because of the Coulomb interaction. So this is for short-range interaction. So the second sound, yeah, is basically the plasma, which is also a coherent excitation, but it's got a gap. So that's the original motivation for the Higgs mechanism, where a long-range interaction can get rid of the Goldstone mode and give it a gap. Okay. All right, so let's proceed there. All right. So we're going to, it's useful to think about this in the grand canonical ensemble. And I'm going to go to momentum space and write the Hamiltonian now. Let's see. Yeah, okay. I have to make sure I got everything right. Okay. So the Hamiltonian in momentum space is sum on k, epsilon k, b dagger k bk, minus mu, sum on k, b dagger k bk, plus u over 2v, sum on k, k prime and q, b dagger k, b dagger prime, b k prime, plus q, b k prime, minus q. So one thing you notice right away is that this thing this expression is what we call normal ordered, where all the annihilation operators to the left of the creation, all the creation operators to the left of the annihilation operators, whereas this one isn't. But when you normal order this, the -1 is just what you need to give you exactly this expression. Okay. So we now, the first thing we want to do is just put everything in the zero momentum. Pick out only B0. So now, from now on, when I put a 0, I mean zero momentum, not the site label. So then what is this energy, including the chemical potential, what does it look like? Well, this gives you nothing because EK is 0. This will give you minus mu B0 dagger B0 dagger.
B0 dagger B0.
Sorry, excuse me. All right, I should actually just to keep. I'll try to follow the notation in my notes. Let me call N0 now. B dagger 0 B0, and so this will be minus mu N0 plus u over 2 N0 times. Okay, I hope I haven't made a mistake here. U over 2V. One. Okay, that's correct.
In the trickle sum, they have all the momentum labels, correct?
Thank you. There's no prime over there. Yeah. Okay, so now the way we're thinking about it, we work in the grand canonical ensemble at fixed mu, and so we have to find the optimal value of N0 at any given mu, and this is the grand energy. So now we just look at the expectation value of the Hamiltonian in this state with N0 particles. This is equal to that, and we want to demand that this is equal to 0. And so that will give us an equation for N0. So this is equal to 0. And when you solve this, you'll find that little n0, which is n0 over v, that's the density of particles, zero momentum state, is just mu over u0. So now what we find is always a macroscopic number of particles, zero momentum state, and that's determined by the chemical potential. You notice this is very singular as u goes to 0. This becomes so mu has to be proportional to u0 in a particular way to get the low density limit. But that's a preferable way to work. All right, so that's another way of restating the very simple facts over here. But now let's go to include the particles at non-zero momentum. Okay. Any questions from the audience?
What is U0, Subir?
Does this work down there? No, it doesn't.
Hi, Subir, can you hear me?
All right, so the next step is to include the particles at non-zero momentum. Include bk at k not equal to 0 and assume they are small. At any given, in some units that will become clear later, the expectation values associated with each such operator is small. So basically, you just take this Hamiltonian, you pull out B0 as special, and then you expand the remaining terms in powers of bk, with k not equal to 0. So when you do that, you get the famous Bogoliubov Hamiltonian, which is H is equal to the leading term, which is minus mu n naught, plus u naught, u over 2 n naught squared. That's exactly these two terms over here. Notice there's a term here, the -1, that we can throw out because relative to the n naught, which is going to be macroscopic, this is completely negligible. So this we throw out. But now they're going to be contributions from finite momentum modes. Those will still be extensive because there's extensive number of momenta. Okay. And so from the sum on k not equal to 0, we're going to get ek minus mu is u and 0 b dagger k. Okay. And it's useful to write it in this way, u and 0 over 2 b dagger k minus k plus b minus k b. All right, so these are the quadratic terms in the original Hamiltonian, while you keep keeping terms to all orders in B0, but only quadratic order at k not equal to 0. Okay, so now, and this is some quadratic Hamiltonian, so the Bogoliubov theory really consists on just diagonalizing this Hamiltonian. But one peculiar thing you notice is that the number of bosons appears to be not conserved. You have terms here that annihilate pairs of bosons and terms here that create pairs of bosons. Whereas the original Hamiltonian preserved the number of bosons. So what's going on here? Well, what's happening is that, of course, when I create a pair of bosons at non-zero momenta, I have to remove a pair of bosons from the condensate. And so there will be two factors of B0 over there that I've just replaced by n0. So here, one further thing I've done is I have replaced B0 and B dagger 0 is approximately square root of n0. So the point here is that this -1 that we threw out was a consequence of the fact that B0 doesn't commute with B0 dagger. But since the number of particles in that state is so large, they're kind of a classical limit, and we can treat B0 and B0 dagger as just classical numbers because the commutator is 1, whereas their value itself is all the square root of n, which is a very large number. So that's where the concept of non-conservation of particles arises. I'm not keeping track of B0 and B0 dagger separately, just replacing them by a number, which is the condensate, the Bose condensate. All right.
Here you're assuming that the thing that has an expectation value is the field itself, like B0.
Yes, yeah. So B0 is condensed.
A number. Yeah, we're not supposed to diagonalize n0, but we're supposed.
Yeah, so we'll do this in a more field theoretical way in a few minutes. First, I want to do it the way Bogoliubov did it, using operators. And the reasoning, Bogoliubov didn't have the reasoning of broken symmetry, which we'll get to. He was arguing in terms of just having the zero momentum modes being essentially classical complex numbers. In fact, more generally, there's a phase here, which I've just set equal to 0, to unity, this factor. And this is the phase that will turn out to be.
I'm just questioning this type of reasoning because it kind of obscures the fact that we have the field, right?
Yeah, well.
If we had diagonalized n0, we would get the different answer.
If you had diagonalized n0?
Yeah.
Yeah.
We wouldn't get the terms that have to.
All right, I agree. This is not the best way to understand things, and I'm going to present the improved way, which I'm sure you'll like better. But this is just to do it the simple way first, and then we'll get to a more sophisticated looking at it. Yeah.
I know exactly where you're heading, but
Yes.
I'm trying to put my head in the framework of the way it's phrased here.
Yeah,
The original system has a finite number of particles,
right,
and B's and B daggers with the commutation relation.
right,
So the system has some n, which is
Correct.
a number. No
Correct.
symmetry is being broken,
yeah,
and the Hamiltonian has to respect that symmetry. Every time you annihilate a particle, you have to create another one.
yeah,
So this description that you've presented here must be an approximation that distorts these basic facts.
yes, so it is an approximation and it's valid in the limit n naught is very large. And it will give you some, if you measure certain correlation functions, it will give you some results that may seem unphysical, that seem to violate the particle number conservation, because if I just look at the expectation value of B0, I'm saying that it's non-zero. Whereas in the real system, it's not. Okay,
But if you just take a box
yeah,
which has some fixed number of bosons,
right,
that number is not going to change.
correct.
You have some Schrödinger problem with these bosons and some symmetric waveframe. The number of coordinates in this waveframe is not going to change.
Absolutely. So that's, of course, yeah. So let me just defer that. That's a great question. That's precisely the next point. But let me just complete this calculation. We'll come to all of that. Okay. All right. So now we just face the mechanical task of diagonalizing this Hamiltonian, which is a quadratic boson Hamiltonian. And that's diagonalized by what's called the Bogoliubov transformation. You just take a linear combination of Bk and B dagger of minus K. So you introduce a new operator. So which are called eta K. So introduce a new set of bosons, which are called eta K. And eta K has the usual boson commutation relation. And you define your BK, the eta K cosh, eta K minus eta dagger minus K times sinh of theta K. So this theta K is an arbitrary parameter right now. And the cosh and sinh have been chosen to ensure that this relation here is compatible with the original relation, which is that BK, B dagger K, commutator is delta K, K prime. Okay, and so that you can easily check for any theta K, these two are consistent with each other. So now you insert this, this operator identity in here, and you expand the Hamiltonian in powers of eta K. And of course, you choose the Hamiltonian so that there's no terms which involve eta, 2 powers of eta or 2 powers of eta dagger. So when the dust settles, and this is something you can work out for your own, you get an answer as sum on K, EK, eta dagger K, eta K. And now this EK is the object I drew earlier. Is epsilon K squared plus 2 U naught epsilon N naught epsilon K. And there's also a formula for theta K, which I won't write it out. It's tans theta K equals something. It's in the notes. And also to obtain this formula, I had to use this fact that mu was equal to mu naught and naught. If you didn't use that, you get an energy that has a finite value at finite K, at any K. But now you notice over here that this thing, as K goes to 0, this is negligible to this term. And when you take a square root, you get this linear dispersion that I promised, sound mode, the second sound mode. And the C over there is just given by this coefficient here. Okay. Now another calculation you can do is you can ask what is the ground state of this Hamiltonian? Well, the ground state of the Hamiltonian is very simple to write down. And this will start to address Nadi's points, I think. So this will, I think, will be a homework problem. Work out the ground state of the Hamiltonian in the B language. So in the eta language, the ground state is very simple. Eta k acting on the ground state must be 0, because capital EK is always a positive number. And so the lowest energy state is obtained by annihilating it with eta k. So then what does this mean in the B language? So this is an equation you have to solve. You have to put eta k in terms of pk, invert that relation and solve this equation. I'll just write down schematically the form of the solution. So this implies that G is equal to, first of all, there's always P0 dagger or N0, the N0 particle in the condensate. But then you're going to get exponential of some on k not equal to 0, some number fk that you'll work out, which depends on theta k, b dagger k, b dagger of minus k, acting on the vacuum of the boson. So the original wave function of Bose and Einstein was just this. And Bogoliubov theory, because of weak interaction, has given us this correction. So you can see what's happening here roughly. There's a large number of particles in the condensate. And every now and then, 2 particles go out of the condensate and go into two momentum states equal and opposite. You create, this has net 0 momentum, and you create particles in pairs at kn minus k. So that's the wave function in this language. But obviously, this wave function has some problems. It seems to have terms with different numbers of particles. There's a term with N0 particles, there's a term with infinite number of particles. We take a very high order term over here. Whereas in a given box, in a real system, the number of particles is fixed. Okay, so this is the ground state in the canonical ensemble, grand canonical ensemble. How do I get a ground state in the canonical ensemble? What is my trial wave function that I should really be using in a finite box? Well, the simplest way to do it is you just imagine you have n particles. You just put a projection operator on the grand canonical ensemble. You just pick out the term, you expand the exponential out, and there'll be many, many terms which have exactly n particles. Just keep those and throw the others out. In fact, you can write down an explicit expression for this. It's an integral from 0 to 2 pi of some angle d phi e to the minus I phi n. And what do you integrate? Well, you integrate this wave function. Let me create an ensemble of such wave functions. So let me change my notation. Let me call this wave function phi. So this is some state with a definite value of phi. And every time I have a factor of b, I put in a factor of e to the I phi. And here I put e to the 2I phi. Okay, so this is actually a valid state, valid ground state solution in the Bogoliubov theory. You can just rotate all the boson by a factor of phi, it won't change anything. The energies will remain exactly the same. So in fact, I had an infinite number of ground states in the grand canonical ensemble labeled by an angle phi, which I arbitrarily set to a constant. So there's a constant phi associated with every Bose creation operator. And then now you can see that this state here, let me call this phi now, is just exactly this state. So this integral will then pick out exactly the state, perform the projection operator and pick out the state with exactly n bosons. All right, so the modern way of saying this is that the ground state of the Bogoliubov theory is a state at fixed phase phi. And if you want to work in the fixed number basis, well, you're free to do that too by just integrating over phi. All right, but the physical in many ways, however, this state is a much, much better wave function than this state. It obeys what's called a clustering property, sometimes called a pure state, whereas this doesn't. So we'll invariably work with this state, and we just have to keep in mind that in reality, there's certain observables that are better computed with the projection. And the other important fact is also, if I'm looking at any kind of local observable, this projection doesn't matter. And this is also something maybe I'll give as a homework problem. It's very similar to the proof in thermodynamics of the fact that the canonical ensemble and the grand canonical ensemble give identical results in the thermodynamic limit. In exactly the same way, as long as you look at local observables, this wave function phi or this wave function g have exactly the same properties as n goes to infinity. Only for certain observables, they're different, but those are typically observable that you're not interested in. Yes?
Do you make any assumption here of how big the index I can be?
The index I?
This thing started with, we had an index I. Position.
Yeah, so that's about an n. Yeah. Volume, that's an n are of the same order. And the index I takes over n values, capital N.
You assume that there's some kind of periodic boundary condition, I assume.
And if you could take any boundary condition you want, as long as you're not looking near the boundary, it's fine. I'm just talking about intensive properties in the bulk. It doesn't really depend what the boundary conditions are. If you're interested in finite n corrections and all kinds of quantum dot type problems where n is not that large, then of course the boundary condition will matter. But in the thermodynamic limit, which is all I'm talking about now, it doesn't matter.
I thought that normally with a finite number of particles, there is no symmetry breaking. And then
Right.
only the bottom state is valid.
Correct. Yeah.
It's only when the number of, not just n going to infinity, you also need the total number of values that I can take should go to infinity.
Yeah, that's also about n. I'm taking them to be the same, of the same order. Yeah. There's a finite density, so it's, if one is 10 to the 23, the other could be 0.1 times 10 to the 23, but they're all scaling together. Yes. Okay. All right, so this discussion brings me exactly to the next point, which historically was first called off-diagonal long-range order. So the question really is, and this was really the origin, of the understanding of spontaneous symmetry breaking, at least in condensed matter physics. I think it also influenced the development of particle physics. Why is this state really thought of something that breaks a symmetry? It certainly wasn't obvious
May I ask
in Bogoliubov's formulation of it, but later on, I think it was Onsager who first talked about what's called off-diagonal long-range order. So this is something very
Can I ask
familiar
one question?
to us today, but it has this peculiar name historically, at least in condensed matter. So to understand off-diagonal long-range order, let's define a field operator psi of R, which is really the same thing as BI on the lattice, but I'll just choose a different notation because we're soon going to use this in the continuum. So this is 1 over square root of V, so 1K BK e to the I T K dot R. Okay, so let's compute the following quantity, which is the correlation function psi dagger of R. And let's do this in the Bogoliubov theory of R prime. We're going to look at this particular correlation function, remove a particle at point R prime and put it back at point R. And if you write things in terms of the density matrix, this is an off-diagonal element of the one particle density matrix in the position basis, hence the name off-diagonal. That's really all that refers to. So this thing you can now evaluate in the Bogoliubov theory. It's just the Fourier transform of some 1K K dot R, that's R prime, B dagger KBK, expectation value. The different values of K prime don't contribute. And this includes all K. So I'll leave the expression for you. It's in the notes. I won't work it out. There's an explicit expression for what this thing is. You can convert it to some integral of some function. And what you find that this is equal to as r minus r prime goes to infinity. This is equal to, in fact, exactly equal to n0 plus some function that decays, plus some function that will decay with some power law. Some number here, some number here, something that decays as r minus r prime goes to infinity. The full function is in the notes. Yes.
Sorry, I don't mean to interrupt, but is it possible to perhaps check? I think some of the students are asking some questions.
Okay, please, yeah, okay.
I don't know if it's.
Thanks. Okay, so one of the questions was, can you mention the motivation to work with the grand canonical ensemble over the conventional Hamiltonian treatment? Yes, the motivation is really, this is a much simpler wave function than this one right here. You don't want to keep doing this projection and these integrals all the time, whereas it's easy to just work in the grand canonical ensemble, we just fix phi. That's a lot simpler than having to do this projection. The other question is, could theta K be a complex number? I don't think so. Theta has to be real, otherwise you lose some homogeneity properties. Right, so the issue of off-diagonal long-range order is that this correlation function, where you annihilate a particle at r prime and create it at r, goes to n0. And just to be explicit, let's say I'm computing this in the Bogoliubov theory in the phi state. Any phi state you want, and compute it, and you'll get exactly the same answer. N0 as r minus r prime goes to infinity. All right, so the fact that there is this long-range correlation, that is, you annihilate a particle over here, and the wave function has some phase over there, and then you put it back somewhere really, really far away on the moon, and somehow the phase there must be the same because you're getting a non-zero expectation value as r minus r prime goes to infinity. Okay, so this is the statement of off-diagonal long-range order. And let's now see from this statement why the phi wave function in some ways is a much better wave function than this g wave function. Let me just call it the n wave function.
So, sorry, Dr. Off-diagonal just means that x isn't equal to x prime or r and r prime?
Excuse me, sorry?
Off-diagonal just means that r does not equal r prime.
Correct, yeah, it's the off-diagonal matrix element of the one particle density matrix in the position basis. Yeah, so that was what's called ODLRO. All right, so now if I look at the statement, I notice a very nice problem, which I want any reasonable theory to have, a sense of locality, which is the statement that that limit r minus r prime goes to infinity of psi dagger of r prime. Again, this is the phi state, sorry. Is equal to phi psi dagger of r phi we have to normalize the state phi for this to be true, but with a properly normalized state, this is correct because this is both; these are both equal to n naught divided by the volume, which is little n naught. Notice this is not the total density; it's the density in the condensate. This is n0, not n. Okay, so and this is nice because it tells you that if I do something here in this room and I do something in India, it shouldn't matter. If it's really far away, if it's the same state, I can just look locally at these expectation values. On the other hand, what if I do this in the n basis? If I take the n particle and I compute this, so this can also be, this is now a more complicated procedure, but I can do it just by using this trick. Once I know the answer for phi, I can do this trick and work out the answer for n. Okay, so when you compute this, you'll find that this is equal to exactly the same value, even in the n basis. So that looks good for this kind of correlation function. It doesn't matter whether you work in the n basis or phi basis. So this is an example of the type of correlator involving some local observable that conserve number of particles that makes no difference at all. And this is actually true for any such local observable. But now the unpleasant fact about the n basis, which you really want to work in, but choose not to, is that this is not equal to n psi dagger of r. And that's obviously the case because this is just zero. If you have a particle, fixed number of particles, you add a particle, you don't get a state with the same number of particles. So in this case, we don't have this clustering property where operators really far away have independent expectations. So that's really why ultimately we prefer to work with the phi basis as long as we have an infinite system. Of course, you have a finite system, then you do have to worry about all of these differences. But that's all I'll focus on for now. Okay. You notice you can take, this also tells you, what's long range. The long range, what has long range order is phi, the phase of the Bose operator. It's the same at r and r prime, and that's long range order. And then now to understand, the physics of the superfluid and why you have, for instance, have this linear dispersion at low energies, you want to consider states where phi is a function of space. Can we imagine state where phi varies as a function of time, where phi is not the same here and there? That's really the heart of superfluidity, trying to understand states where this phi can vary in space. That's a little tricky to do in the Bogoliubov formulation, but it's much easier to do in the path integral formulation, which is what I'm going to now turn to. Okay. And also this, this phi can have any value. The physics is independent of the value of phi. So any given system chooses some value of phi. So if you have a superfluid with some value of phi, well, okay, it's chosen a value. That doesn't seems like it done much. It's just an overall phase of the wave function. But if you bring two superfluids together, they could have different values of phi. And the difference in phi are physically meaningful. And therefore, the choice of phi that you made is sometimes called, well, usually called spontaneous symmetry breaking. You've broken a symmetry which is associated with the rotation of the phase of the Bose operator, which is essentially the symmetry of conservation of number of particles. Again, I emphasize that doesn't mean the number of particles is not conserved. It's still conserved. It's just that this basis in which you don't conserve the number of particles has its nice clustering properties of observables. Okay. Any questions? Look at the chat. All right, great. So now I'm going to do all of this again, but in the path integral language. And that's really very useful for many other things we're going to do. We're going to, once we get to more complicated systems of bosons with more complex interactions, we look at phase transitions. Then the path integral language has much, is a lot more convenient. And even for an ordinary superfluid like this, it's much more convenient to think in the path integral language to talk about states where phi is a function of position or time. Those are some non-equilibrium states that you could impose by bringing two superfluids next to each other, putting pressure on a superfluid, applying a magnetic field if the boson were charged, and so on. So these are things we want to be able to do, not just look at the ground state of a completely uniform system.
And is this psi of r up to a factor just your original BIs?
Yes, it is. Yes.
And the factor is what, the root time?
No, I think it's just 1 over the volume of the unit cell of the lattice space. Yeah, sorry. So the psi, yeah, I should mention in the notes. The only difference between the psi and the V is that the commutator of V and V dagger is a delta, Kronecker delta, and the commutator of psi and psi dagger is a Dirac delta. But that just gives you a volume of the unit cell. Okay, so now let's redo this whole song and dance, but using a path integral language for exactly the same theory. But this whole picture, really was the origin, as I said, of the whole understanding of why is a superfluid a state of broken symmetry, how that broken symmetry is responsible for superfluidity itself. And then once you add long-range forces for the Higgs mechanism, which we'll get to eventually. Okay, so now let's do the same theory in the path integral language. And I'm just going to go ahead and work in the continuum. This is not yet for the Bose gas. We'll get to the Bose gas, the Bose-Hubbard model a bit later, probably not today. What time is it? 10 of 10. Okay. So let me just write down the theory that we're going to look at. So the partition function in the now I'm just working in the grand canonical ensemble, which is e to the minus beta h, is a path integral of some complex field psi of space and time. This is imaginary time now, of some action e to the minus an action, and the action is the following. So if you have finite temperature, that everything is periodic in time. So psi of r and beta is psi of r at 0, and here beta 1 over temperature, v tau. Okay, it's very simple. Psi star psi v tau. I'm just going to take a quadratic dispersion. So we drag psi squared 2m. We have a chemical potential minus mu psi squared, and the contact interaction.
Hello.
With unit lattice spacing.
Hello.
Psi to the 4th. So if you're, I hope all of you have had a chance to look at some notes on coherent state path integral. Actually, I realized I also have some notes. I'll put them on the website, but there are many textbooks. This is just the coherent state path integral. We are writing down the same Bogoliubov hamiltonian in the continuum for now. This particular term is just the path integral way of representing. There's also an integral over space, and I'm going to work in d dimensions of space. This term is simply the path integral representation of the fact that psi of r, psi dagger of r have a commutator. And this term, you should also note, is a complex, it's purely imaginary. It's a phase factor, sometimes called a Berry phase, that appears in the path integral. It's different from the ordinary Feynman path integral of particles, where if you do it in position space, you get a purely real action in imaginary time, kinetic energy plus potential energy. But if you do what's called the phase space path integral over p and x of a particle or a harmonic oscillator, then you will get such a term, which will be analog of that term will be pq dot for a single particle. Okay, I'll put some notes on how that's derived. Okay, so this looks like a very complicated path integral to evaluate. But the general trick we're going to use over and over again when we face with path integrals is use the saddle point method. If you're going to find some stationary point where over this configuration space where S doesn't vary, has a saddle point of some type, study that saddle point and then do Gaussian fluctuations about that point, and that will pretty much, so all you really need to do in the end is some kind of quadratic path integral, which is similar to just doing the integral, diagonalize the Bogoliubov Hamiltonian, as we'll see. All right, everything okay there with the TV and the broadcast?
Mhm.
Okay. All right, so as I said, how do we proceed? Well, you want to look at a saddle point. So we look for the saddle point. So the path integral of the psi, and so you just want to solve ds d psi equal to 0. And we want to do this, we're going to assume that it's space and time independent, x and tau independent, saddle point. The psi is just a complex number then, and this thing disappears, this also disappears, only these two matter, and therefore you have minus mu, sorry, what have I called it? Okay, minus mu psi squared plus u over 2 psi to the 4th, 0. And this tells us that psi, and I'm going to write it this way, is square root of n naught times e to the I phi, where n naught is the old n naught, which is mu over u. Just diagonalize this quartic polynomial, and this is the answer. And now I'm explicitly using phi here because this only involves the modulus squared, and this phi will be exactly the phi that I had there earlier in the operator representation. All right, so that's the saddle point, and then now we want to look at quadratic fluctuations, expand the action around the saddle point, and see what you get. And that's entirely equivalent to what Bogoliubov did. But this is, as you can see, a lot neater. We're not making any assumptions of k equals 0 and k not equal to 0 and all of that. We're just doing an honest path integral where we're just doing the path integral by the saddle point method. All right, so we want to look at fluctuations about this. Let me call this size 0 here. So how do we parameterize the fluctuations? Okay, so we'll take our psi of r and t. There's many ways to do it, but this is the more conventional and elegant way. I'm going to take it's a square root of n0 plus n1 of r and tau, and e to the I phi of r and tau. So when phi is a constant and n1 is 0, then I have the saddle point. And now I look at fluctuations about it, and I allow them to be both space and time dependent. The reason I've written it this way is now you can see that this n1 is precisely the local density fluctuation, and phi is the phase. And this we're just going to insert this into the action and expand to quadratic order n1 and phi. Okay. Right. The other interesting thing you can check for yourself that this measure of the path integral is also very simple in this way of doing it. And up to normalization, d psi d star is just dn1 d phi. Okay, so the only approximation really is the fact that n1, we're going to integrate n1 from minus infinity to infinity. But of course, we can't do that because the square root has to be positive. And so there's a lower bound on these fluctuations, which we're going to ignore. So that's the one of the approximations, other than the fact that also we're going to expand to quadratic order and 1 and 5. Okay, so you just insert this in there and see what you get. So then the action is some 0 order term that we already know, write out. And then you get the remaining terms which are quadratic.
Hello?
Okay, so the first thing is that this term
Here, where?
now becomes explicitly imaginary. And it's the following, it's n1 times d theta d tau. Well, d theta or phi, sorry, my notes have theta. Well, okay, I'll stick to phi today. D phi d tau. So that comes directly from this term. There are some other terms that integrate, once you use periodic boundary conditions, give you a constant. Won't worry about those for now. So what does this tell you? This is very much like PQ dot in a path integral. It tells you that phi and n are canonically conjugate. The phase of the condensate is canonically conjugate to the density fluctuations. So the time derivative of the phase is something like a density. And that's, of course, crucial for various things, including the Josephson effect. Anyway, so this is what you get from this term over there. And the other terms are now, in fact, we can work it out to all orders. I'll only write down the quadratic terms. Yeah, so you will get that's 1/2 u naught plus k squared over 4n naught times, okay, now I've gone to momentum space, sorry. N1 of k squared. So this is the cost for energy, for density fluctuations. There's a cost u naught for a uniform density fluctuation. That's telling you that it's a compressible system. And then there's the most important term, which really explains the presence of a linear dispersion, is this term that depends upon theta, which is n naught k squared over 2m times theta of phi, sorry, excuse me. Phi sub k squared. So what you notice here is that if phi is a constant as a function of position, then because of the k squared here, there's no energy cost. So slow variations in phi cost an energy which is proportional to the gradient of phi squared. Now we have some understanding of what phase fluctuations spatially look like. A spatial fluctuation of phase, give you an energy cost is proportional to the gradient of the phase squared. The coefficient, when you go to some renormalized theories, often called the helicity modulus of the superfluid density. And time fluctuations of phi are canonically conjugate to n1. Yes.
U naught is u.
Yes, sorry, thank you.
Sabir, can you hear this now?
Okay. All right, so now you can, you can view this. You can just.
Can you hear my voice coming out of the TV, Sabir?
Relation, because this is precisely the path integral of a harmonic oscillator, one harmonic oscillator for each momentum k. This is like the n is like a momentum. So this is like a p squared over 2m, where the mass is some number. You can ignore this k squared because you're looking at long wavelengths, so it's just some constant. And this is the displacement of the harmonic oscillator with an energy that goes as k squared. And this just tells you that position and momentum are canonically conjugate. So from this, just by mapping the harmonic oscillator, you can just read off the dispersion. Or if you're still more of a functional person, you do one more integral. You do integrate over density fluctuations. And then you'll get a even simpler theory. So now let me do that over here. So I actually do the integral over n1. And then I get a path integral, just an integral over theta. What will be the action
Is
of
the
theta?
audio working now?
Yeah.
What will be the action of theta then? I'm running out of white chalk. So as theta Well, you just do the path integral over N1, and you do that by just completing the square.
Just to check, you mean phi, right?
Sorry, phi. Excuse me, sorry. This is why I should have changed notation in my notes of theta. So I just complete the square and just do then do the Gaussian integral N1. I'll get some dependence on phi. Just by looking at this, you can see what you're going to get is just d phi d tau squared times the inverse of this. So this is going to be something like this. And sum on k integral on d tau. So you have d phi dk d tau squared. And I'll throw out this k. It's not important. It's in the notes if you want to keep it. Times 1 over 2 u naught plus n naught over 2m. Actually, let me just make everything in space and time. Or d phi tau squared. And this is grad phi squared. And this is integral over space. Okay. So now that's a very appealing looking theory. It's the theory of a relativistic scalar field. Oh, sorry, I wrote it twice. This k there. Okay. So it's a massless relativistic scalar field with d phi d tau squared and grad phi squared. And this from the values of these numbers here, you can read off the value of the velocity of sound. All right. So we started with the non-relativistic Bose gas. We condensed the particle in the ground state. We integrated out the density fluctuations, and that gave us the theory of a linearly dispersing sound mode. Yes.
How is this observed experimentally by the existence of this mode? By thermodynamics or by looking at long-range correlations?
Oh no, you can actually see pressure waves. So you can, depending on what frequency you look at, you can see just like, so the experiments are very similar to experiments you do to detect sound, ordinary sound. But these occur in a different frequency and momentum range than first sound, which is at much longer wavelengths at finite temperature. At zero temperature, this is the pure infinitely long-lived mode. This is all there is. Yeah. Okay. Right. So let me draw another picture of this, and also draw a contrast with things you may have heard. So let's take this potential over here. Where did it go? Here, this potential, and actually make a picture of it. So what have we done? So if I draw V of phi, that has the form of the famous Mexican hat potential. So this is psi, which is complex number, and so V of psi. So that looks something. This is 0 here. Looks something like this. With the Mexican hat rim over here. Okay. And I'm just plotting this function here. This function here is V of psi. So what have we done? Well, what we did was we condensed a particle here. We took psi at some point along the bottom of the rim. And then we looked at fluctuations about that point. And there are two types of fluctuations. There's the fluctuation in this direction, which I call N1. And then there's the fluctuation along the rim of the hat, which I call phi. Okay. So these we found, were expensive because there's a constant over here. So we integrated them out and we got a theory for these phi fluctuations. which is the second sound mode. And so now you also notice something very important here, which distinguishes this.
It's something I don't understand here.
Yes,
I would understood what you just said if you had a second order in time action.
yeah,
But N1 is not really an independent mode of phi. It's
Correct.
a conjugate.
that's right.
So you didn't really integrate out anything. You just wrote it in second order formalism rather than first order formalism.
Yes, you're right. You're correct. I misspoke. I mean, or I wasn't precise enough. Yeah, I didn't integrate out any degrees of freedom. I just went from a phase space formulation to a coordinate space formulation of the path integral.
And once I interrupted you, I had one
Yeah.
more. In the top blockboard, you have a sum over K,
Yes,
which I interpret to mean that you work in finite volume. Where
you can make it an integral, okay, if you want, then you have to, there's factors of volume and so on. Yeah, but right now
but the physics is completely different because in finite volume, the symmetry is not broken. In infinite volume, it is.
right. So in at least for this lecture, I'm just always referring to infinite volume case, and I'm writing expressions in finite volume and taking implicit limit of the finite infinite volume limit. Yeah. All right, so what I was saying was that there, as Claudia correctly pointed out, N1 and phi are canonically conjugate. There's only one mode here, which is this phi fluctuation. Now the situation is very different for a relativistic scalar field. If you take the Higgs theory of a scalar field and ignore the gauge field for now, you'll get the same picture, except you'll have a second order time derivative. You won't have this term here. You'll have a term like d psi d tau squared. So when you go through the same procedure, then you'll find a very different answer. You still get, at least for this theory, you still get this phi mode with the linear dispersion. You still get the Goldstone mode, but you get another particle with a finite energy, and that's the Higgs boson, this longitudinal fluctuation. But that's only present for the relativistic case. That's not present here for this non-relativistic Bose gas, because the density mode is just canonically conjugate to the phi mode. Okay. And of course, in the true Higgs mechanism, there's long-range interaction, and so the phi mode disappears and becomes a W&Z boson in the theory of weak interactions. Or if you have a charged superfluid, the phi mode becomes a plasmon. So plasmon is the analog of the W&Z bosons. Really. Okay. All right, so that I've covered a lot of ground here. This is basically reviewing the theory of the weakly interacting Bose gas in the continuum. There's only one ground state. The ground state is always a superfluid, at least for weak interactions. And that superfluid has a very simple excitation spectrum. At low energies, it has a linearly dispersing phase fluctuation mode. And that's all there is to it. Okay, now you could imagine that in the continuum that, could you get anything else? Well, if you take the real system like helium-4, which just lives in the continuum, you do get under pressure, helium-4 forms a solid. And that involves breaking translational symmetry. And that can happen. That's in principle a property also of a path integral like this in some high density limit. But that's very hard to study, and it tends to be a very strong first order transition. And so we won't go into that. Another possibility you could imagine happening in the continuum, what if U is attractive? You could imagine a situation with the interaction such that two bosons like to form a bound state, but then pairs of bosons, the molecules repel each other. Then you get a situation where the pair of bosons Bose condenses. That is still a superfluid, but it's a slightly different superfluid. It's a superfluid of pairs of bosons, not a single boson. And the way you see a difference is that the vortices, the quantization of circulation in the vortex, the quantization of circulation in the condensate is different from that we've talked about here. We'll get to that later. Okay. But the basic answer is in the continuum, nearly always, the ground state just is superfluid. So to get something else, some other new type of ground state, we really have to go back to the lattice. That's the simplest place where you can see other ground states appear at large U. Yeah, so that reminds me. So for helium-4, U is not small. And so, but nevertheless, the theory is that I presented is still morally correct. And let me just make a few remarks on that. This was a quite important and source of much confusion. So,
is it a right time to ask one question?
yeah, sorry, go ahead. Yes, please.
In the canonical ensemble, it naively feels that the number conservation is not violated. Can one argue from the Goldstone theorem point of view about the gapless mode, or there is some other argument about the gapless mode?
Well, okay, so it depends whether you're talking about infinite volume limit or not. I mean, those are two different things. You have to distinguish canonical versus grand canonical ensemble from whether you're truly in an infinite volume limit or not. If you're truly in the infinite volume limit, there's no difference between the canonical and grand canonical ensemble. And you can work in either way you prefer. You can certainly go through these arguments in the canonical ensemble. You'll just find that it's more complicated, and in the end, it makes no difference. And there'll be some problems in the homework where you'll see that. But if you're in a finite box, then yes, then what happens is that this Goldstone mode gets split into a discrete set of modes, and the energy splitting is roughly proportional to the inverse volume of the box. Basically, what we have to worry about in a finite box is just a single rotor variable, a single phi, which is the zero momentum component of phi. So that zero momentum component behaves like a rotor, like a particle on a circle, whose mass is proportional to the volume of the box. So it's a very heavy particle and has very finely spaced energy levels, which are kind of the remnant of the Goldstone mode.
So this gapless mode so the Goldstone theorem still holds in the canonical ensemble, even if the symmetry is not broken in the infinite system limit. Is that the statement?
No, I would think the correct statement would be that in the infinite volume limit, the symmetry is broken in both ensembles, and the Goldstone theorem holds.
I see. And what symmetry is broken in the canonical ensemble? It is definitely probably not the number conservation. Some other symmetries.
No, I think this. Yeah, I'm sorry to be. I have confused things maybe a little bit, but it's more of a semantic problem. I think the conventional terminology is we consider the symmetry broken in the infinite volume limit, and it's more of a technical choice whether you choose to do the calculations in the canonical or the grand canonical ensemble. But the technical choice of the grand canonical ensemble is invariably a lot simpler because it has this clustering property.
Okay, thank you.
Yeah, so you get into all, you tie yourself in knots if you don't have your theory that doesn't have the clustering property. And then what it means by a broken symmetry or not may be a bit confusing. So I think it's maybe my preference would be just work in the grand canonical ensemble, and then things are clear. And then check that the answers in the canonical ensemble are also the same. But the conceptual framework of symmetry breaking is obviously much clearer in the grand canonical picture. All right, what was I going to say? Yes, so we have a superfluid state. And there's two different quantities that characterize it. One quantity that is, so it has a Bose condensate. And what that means is that the expectation value of B0 or B dagger 0, B0 is some N naught over V. Okay, and the important point is that N naught is not equal to N for U not equal to 0. And indeed, you can, in helium-4, N naught, is like 10%. It can be very much less than N for large U. So the size of the condensate itself, which is just a measure of how many particles are in the zero momentum state, can be quite small. Okay, but there's another separate characterization, which I'll call the superfluid. I'm going to call it the stiffness. It's often called the density, but that's really very confusing in the cases where you don't have continuous translational symmetry and Galilean invariance. So what is the superfluid stiffness? The superfluid stiffness you would define the following way. You take some state phi, but you allow phi to be a function of position. So this is some slowly varying state phi of R, where phi is different at different points in an infinite volume. And you look at the changes in energy. So what is E minus E naught? What is the energy of this phi state? Whereas the phi E naught is the phi constant state. What is this equal to? Well, since the theory is local and you're really making very long wavelength deformations of phi, you would say that this is some integral over all space. And then you have the gradient of phi squared. And there's some coefficient. And that coefficient I'll call rho sub s over 2. Now this is a perfectly well-defined equation. This is units of energy. Phi has units of well-defined. It goes from 0 to 2 pi. You can't rescale it. It's the phase of the wave function, whatever it is. It's a dimensionless number. So rho sub s is a perfectly well-defined quantity for a superfluid. And in fact, in the Bogoliubov theory, we got some value from this. We can work it out what this is, what this number of rho sub s is. And the dimensions of rho sub s, you can just see from here, are energy times length to the 2 minus d. So those are the units of it. So in 2 dimensions, it has a spatial dimension, it has the units of just energy. In 3 dimensions, there's energy per length. And that's why I'm not calling it a density. If you read old books on helium-4, you say there's a superfluid density. It's not really a density, it only becomes a density when you put strange things like h bar squared over 2 over m over here. Where what m do you put in here? Well, if you have Galilean invariance, it's clear what m. But if you don't have Galilean invariance, it's not clear what's m. So it's much cleaner to just not put that there and talk about this quantity, which is perfectly well defined. All the lattice are in the continuum. Okay. So now the question is, what is this quantity, rho sub s? So for the Bogoliubov theory, if you work it out, it has a very simple value. Let's see. I haven't written it out, but see if I remember. Let's see. I'll read my glasses. Yeah, so for the Bogoliubov theory, if you look at what is the value of rho sub s, rho sub s turns out to be the total density to leading order total density h bar squared over 2m, where this is the bare mass of the bosons and n is the total density. Okay, so this is the case in the Bogoliubov theory. For weak U, so this is for U, it's U much less than some units, 1. Okay, so now in helium-4, however, U in whatever units you choose to measure it is not small. It's in fact huge. It's a hard sphere and the gas is very dense. It's not a dilute gas, it's a very dense gas. So what do you expect? Well, we already found for small u that there's what's called the depletion of the condensate. Not all the particles in the condensate, there's a correction associated with the exponential part of the wave function that I wrote down. And so for large u, we can expect that this is true. The condensate disappears. And in fact, in helium-4, it's about 10% of the particles when you measure it by neutron scattering. The number of particles in the condensate is very small. So the number of particles in the zero momentum state is very small. On the other hand, if you measure this quantity, rho sub s, now in the simplest theory, that's also proportional to the density of particles, which is also the density of particles in the condensate. But there you find that this could be completely different. In fact, in helium-4, this result is actually exact with Galilean invariance for any u. So in some sense, helium-4, even though its condensate is so weak, is a perfect superfluid at zero temperature at T equals 0. So I'm not going to prove that, but anyway, you can look at the structure of the action and what we've defined and see that this is the case. So sometimes you often see that, especially people with cold atoms making statements that, well, they found a weakly interacting condensate, but the condensate is large and it's a better superfluid than helium-4. And in fact, that's not true. Yes, the condensate is very small in helium-4, but the superfluid density is still actually the maximum value. It doesn't go down. And so this sort of emphasizes that when you make a change of phase, and I showed earlier, you're changing not just the phase of the condensate, you change the phase of every particle. Really, the whole ground state is a superfluid. Every particle is associated with the change in phase. And this quantity, the superfluid density, is something you measure in some experiments involving, flow of current, a flow of, for example, in the charged superfluid, this is the quantity that appears in the London penetration depth, how the system responds to a magnetic field. That's involves rho sub s and not n naught. All right, so that's just a little aside to say that this theory, although a theory for weakly interacting particles, is in fact a perfectly good theory for helium-4, apart from not getting the numbers right. Qualitatively, it gives everything correct. And this was the source of a lot of confusion and arguments, very bitter arguments in the 60s by many famous physicists. Yes. Yeah.
Rho sub s is rigorously defined.
Yes.
But is n0 really rigorously defined?
Yes. You do a neutron scattering measurement. You look at the structure factor and the zero momentum the forward scattering amplitude will give you n0. So you measure, you have a superfluid, and then you send in some neutron or some particle that couples to the density. So you have your density of particles that couples to some source. We call it
And
H.
the neutron scatter from a particle in an excited state?
Yeah, so you measure the density correlation functions. What neutron scattering cross-section measures is the n of r tau n of 0, 0. Times e to the I k r minus omega tau. So by looking at the neutron scattering experiment, you can measure this quantity s of k and omega. Okay, so that will give you, let me just even integrate over all frequency. You do inelastic scattering. And s of k, the structure factor, you can measure s of k and omega too if you want. Well, anyway, s of k and omega has a term delta of k, delta of omega times the condensate plus some regular part. So this part will be the inelastic terms, so that certainly will be there, but there'll be a delta function, forward elastic scattering contribution, that will give you the value of n naught.
This is surprising because in analogous problems in high energy physics,
Yeah.
the condensate is not well defined, whereas
Because you have a gate charge. Here, there's no gate charge.
even without gate charge.
No, it's well
So
defined.
in QCD, the first thing is psi bar psi, and rho sub s is what we call
Well,
phi square.
Right, exactly. So I was going to say
Phi
that.
square is well defined, but psi bar psi depends on the regularization scheme, and all sorts of other things. I guess this is what Edward had in mind when he asked the question.
Yeah, so I think the point is that this is a theory which is UV finite. It's just, the Hamiltonian Rodin with the first order time derivative is perfectly finite. The notion at very high energies, this theory of just free particles. You know the spectrum completely. There are no vacuum fluctuations of antiparticles here. But even if there were, this still would be well defined. I think psi bar psi. Yeah. I mean, there may be, because you also have some bare quark masses, but suppose you had a theory with no bare quark masses, then I think correlation function of psi bar psi would be well defined. If you actually broke chiral symmetry, I think this is a gauge invariant order parameter, and it has a well-defined value. No, okay, we can discuss that.
Depends on the scheme.
Okay.
Well, I wonder if you'd measure the same nonzero with neutrinos as with neutrons, if you could do it. In other words, that's a way to ask whether.
Yeah.
Remember, you've defined something, but it might depend on the probe,
Right.
not just on the system.
No, I don't think so. I think, okay, maybe the answer is that there's no infinite Dirac C here. When you're doing relativistic fermions, you have the infinite Dirac C to worry about. There's no such thing here. I mean, if you did the same thing from graphene, you would bottom of the bag and so on. Okay, great. It's time. Any questions online? India. Elliot, you have a question? Oh, you should mute yourself.
Oh, sorry. Whoops. May I ask a question?
Yes, please go ahead, Elliot.
About this question that came up earlier about the C number substitution of A0 or rather B0 by a C number and so on, and whether this is legitimate and so on. Let me just mention that what we proved back in 2005 in the Physical Review letters is that the C number substitution is perfectly rigorous in the thermodynamic limit, in the sense that it makes a mistake in the energy of the order of 1, not of order n. And you can moreover do this for any number of operators you want, not just B0. You could take any of them and substitute in a C number. For each time you do this, you make a mistake of order 1. So don't do too many if you want to get the right answer. And the rule is you have to do this consistently. That is, every time you see this operator in your Hamiltonian, you do it consistently. You don't substitute sometimes and not other times. I mean, you consistently substitute. And after you've made the substitution, you then compute, if we're talking about the ground state energy, you compute the ground state energy in this new Hamiltonian where you have the C numbers, and then minimize the energy with respect to the C numbers. In other words, you regard them as parameters, and you minimize the energy of the resulting quantum Hamiltonian with respect to these parameters. If you do that consistently and correctly, then you get the right answer in the thermodynamic limit, and end of story. I mean, that's completely rigorous. And using coherent states, you can prove this.
Okay.
I mentioned this in case this is of interest to anyone.
Yeah, if you can maybe put the reference to your paper in the chat, I'm sure students will be
Well,
able
I
to.
can give you the reference if you want. It's in 2005. Where is it?
I'll dig it up.
Review letters. You'll find it.
All right, thank you. Thank you. Any other questions from the students? All right, great. So the notes are on the website. We'll try to get a homework to you. And see you on Monday.
we clap in the course or not?
No.
I have another question.
Okay,
I
sure.
decided to hold myself, so I asked you.
Let me put my mask on. Let me put my mask on.
Yeah, so many people.
Yes. Oh, this is great.
So two things. So imagine you write this thing, which is first order.
Yeah,
But you think of it as an expansion in the number of derivatives, so there are higher
yes,
derivatives.
there are, correct.
And then among the higher derivatives, there's also a second order term.
That's right.
So in that case, there is an N-like mode,
Yes, yes,
except that it's heavier.
correct. And we are coming to that next lecture.
You will come. No,
Yeah.
but even in this system, it exists, but it's high order. Even in this system, if you add,
Well, I think if you have Galilean invariance, it doesn't. The Galilean invariance kind of tells you that this is all.
well, I'm
you've
sure
got.
there are high derivative terms that are invariant under Galilean.
Okay, yeah, but, all right, you would have to be very careful about that, but I don't know if you'll get, something like a Higgs boson at some
I
high
am
energy.
almost certain you will.
I don't think so.
No,
No, you need to be on a lattice or something.
no, you have to regularize it, but
Well, no, but it's all, I'm saying if you write this, you don't need regularization if you have Galilean invariance, it's defined on the continuum. The continuum theory with Galilean invariance, I don't think has the analog of the Higgs boson.
I'm almost certain there is. Well, I had exactly this, I had this position and Michael Peskin convinced me I'm wrong.
Is that right? Okay, okay. Well, on the lattice, I agree with you. I will see, in fact,
Yeah,
that's going to
it
play an
exists.
important role in what we're going to talk about. But,
Yeah, it's also, you shouldn't call it the Higgs particle because,
okay, what should I call it? The Anderson particle?
no, it was even before him, it was in, oh, wow, we can get to the history. I actually studied the history of this extremely well.
Yeah.
The other question is Luttinger's theorem. Is it
Yes.
Luttinger or Luttinger? I don't know how to pronounce it.
I don't know. His first name, what was his first name? Joaquin or something like that.
So the way you wrote it, I think you need a factor of the volume. In the way you wrote it in your slides.
Yeah, I mean, I was a bit sloppy. I was talking about density per unit cell. The fact of the volume of the unit cell, there is
okay.
what's missing.
Okay, that would answer my question.
Right, yeah, yeah.
Because you wrote something like the density mod 2.
Yeah,
And
the
you made
more,
a big and you made a big point of the dimensions.
Yeah. right. So if you're in the continuum, you don't need the mod 2, and then everything is defined in density per unit volume, and everything and KF is. But if you are on a lattice, the density has to be divided by the volume of the unit cell, or multiplied by the volume of the unit cell.
Okay, that answers my question.
All right, yes, I should correct that. Yeah, yes. Yeah.
Sorry, we gave you a hard time because
No, this is good.
I'm kind of constantly trying to translate it to things.
No, I think it was
And
very good.
when I managed to translate, that's fine.
Anyway, okay, I'm pretty sure this is right. I mean, you need to know the matrix element, of course, of your probe.
No, so this is this point, the analogous problem is that if you do QCD,
Yeah,
the symmetry is spontaneously broken,
right.
then psi bar psi.
No, but this is not, yeah. Okay.
This is the analog of your order. This is the order parameter.
Yeah,
In its case, like lambda QCD cube,
right.
but the number that sits here depends on what you mean by lambda. And also depends on what you mean by psi bar psi.
Right.
There's no preferred definition.
Yeah, so there
This
is
is to be contrasted if you write this thing
right.
for the pions. For the pions, this is completely meaningful. This is 100.
Right. So now the point here is that, I think another way to state it, that this phase pi field is a dimensionless field that has no wave function normalization.
That's right.
Whereas here, psi bar, psi, and psi have some wave function normalization that depend on and that comes from UV divergence from the preference of the rag C. There are no such normalizations here.
Well,
The UV structure of this theory is just, the UV field is just B.
Right.
You know it fully. There's
Yeah,
no
but if
normalization.
you add high derivative terms, or if you add high dimension operators, they will probably change. The answer for this is universal. The answer here is not universal.
Well, I think what happens is that,
And I'm almost certain that this is what Edward.
okay, I'm not allowed to add, okay, what I'm not allowing you to add are higher time derivative terms. These are canonical boson. You can add any special derivatives you want, but I'm forbidding any higher time derivative.
Then you might be, then it might be okay.
And what happens is that any kind of closed loop graph, because it has an I omega in it,
Yeah.
just gives you zero. So all of those UV.
I'll have to think about that.
Yeah, so I'm certainly forbidding any time derivative terms. The canonical boson in the UV. That's an
Okay.
assumption.
This is wonderful. This is wonderful. I can't wait till the next lecture.
Okay.
So I woke up early this morning and the first thing I did was to go through the notes from
All right.
the first one.
Okay, great, thank you.
That's great. Will we talk today? It's also a good meeting.
Oh, yeah.
Today after lunch. We should also talk.
Hi.
I've been communicating with Uta about the talks we're giving.
I have another meeting.